in the last video I was saying that the z-scores that are up at the upper boundaries are the confidence coefficients. So the z-score at the upper boundary of the middle 80% is the 80% confidence coefficient, and the z-score at the upper boundary of the middle 60% is the 60% confidence coefficient. These were the 80% and 60% confidence coefficients in the example we did in the last video. And we can see here that if the possible samples followed a normal distribution, if they followed this type of shape, then the 80% confidence coefficient would be this number right here, and the 60% confidence coefficient would be this number right here. Because if the possible samples follow a normal distribution, in other words, if the sampling distribution is normal, then this z-score will be at the upper boundary of the middle 80%, and this z-score will be at the upper boundary of the middle 60%. So what we have here are just the confidence coefficients for each percentage. We have the confidence coefficient for each of these percentages in this left column right here. So this z-score right here of 1.645 would be the z-score at the upper boundary of the middle 90%, and this z-score of 1.96 would be the z-score at the upper boundary of the middle 95%. So I'll label these right here. So next, let's think about in what situation would the sampling distribution follow a normal distribution? Because obviously we can see that in my last example it didn't follow a normal distribution. So let's think about when would we have an example in which the sampling distribution would be normal. I'm going to switch to a new slide to talk about that. First, let's look back at this slide from the last video. In this example, we had a population of 4 people. These were their 4 ages. And right here was a histogram of the population. This is just showing the ages of the 4 people in the population. Here we had the sampling distribution of the means of all possible samples of 2 people. And this sampling distribution followed a different shape than the population. And we also had another sampling distribution for the samples of 3 people. So what this histogram was showing is the means of all possible samples of 3 people, and there should actually be 4 boxes on here. I think this is an incomplete version of the slide from before I was finished, but we had 1 box at 25, 1 for 25.67, 1 for 26.33, and 1 for 27 right here. So this sampling distribution for this sample size had a flat shape, just like how the population had a flat shape. So now we reviewed the difference between the shape of the population and the shape of the sampling distribution. Now let's go to this slide right here. If we're sampling from a much bigger population, then the shape of the sampling distribution is actually predictable. It's predictable based on the shape of the population and the sample size. Let's imagine that this is the population of a city. So maybe the city has 20,000 people, or maybe 100,000 people. And let's also imagine that this population has a normal distribution, like this. Maybe we're interested in the ages of the people in this city. So let's imagine that the ages of the people in this city's population have a normal distribution, meaning most people have ages in the middle and fewer people are at the tails. And what if we wanted to select a sample of 10 people from this population? Maybe we're interested in the heights of the people in this population. So let's say that the heights of the people in this city's population follow a normal distribution, meaning most people are somewhere in the middle, and there's fewer and fewer shorter people and fewer taller people. And what if we were taking a sample of 10 people from this population? Well, if we took a sample of 10 people, we might get this person, maybe this person. We would just get a selection of 10 people. So let's see, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if these were the 10 people in our sample, we would be recording the heights of these 10 people, and then that would be our data set. But remember that this is only one possible sample of 10 people that might be selected. There's other possible samples that could have been selected. For example, we might have ended up with this sample of 10 people. So there's actually many possible samples of 10 people that could be selected from this city's population. And each possible sample of 10 people will have its own sample mean, because if we added up the heights of these 10 people and divided the total by 10, we would get the mean of this sample. And then if we added the heights of these 10 people and divided the total by 10, you would get the mean of this sample of 10 people. And every possible sample of 10 people has its own sample mean. And those sample means would follow a normal those sample means would follow a distribution. And the distribution that they would follow in this case is actually a normal distribution, because there's actually a rule that if the people in the population have a normal distribution, then the sampling distribution of possible samples also follows a normal distribution. So we're saying that this is the sampling distribution for n equals 10. Meaning we're saying that if we wrote out every possible sample of 10 people that could be selected from this city's population, and we calculated the mean of all of those possible samples, and then we put those means into a histogram, it would the histogram of possible samples would follow this shape. So if the population is normal, the sampling distribution has to be normal. And if the population is normal, the sampling distribution is also normal regardless of what the sample size is. So if instead of creating a sampling distribution for the sample size of 10, we decided to create the sampling distribution for the sample size of 20, we would still get a normal distribution. In other words, if we wrote out all possible samples of 20 people that could be taken from this population, and we calculated the mean of each of those possible samples of 20 people, and then we made a histogram with those sample means, that sampling distribution would also be normal. So if the population follows a normal distribution, then the sampling distribution is normal regardless of how many people are in each of the possible samples. What I mean is regardless of whether it's a sampling distribution of samples of 10 people, or a sampling distribution of samples of 20 people, or a sampling distribution of samples of 15 people, the sampling distribution is always normal if the population is normal. So this was for n equals 20. If I wrote out every possible sample of 30 people and calculated the mean of each possible sample of 30 people, and then created a histogram with those sample means, then that histogram would also be normal. Because I said that if the population is normal, then the sampling distribution is always normal, regardless of what sample size you're dealing with. Now what if instead of following a normal distribution, what if the heights of the people in this population follow the skewed distribution, meaning a distribution that's skewed to the left or skewed to the right? Well, then we would see a different pattern in here. And I'll show you what that pattern would look like. Let's say that the population is skewed instead of normal. Let's actually say that it's skewed to the right, meaning there's a lot of shorter people in this population and fewer taller people in this population. Now let's think about what would happen if we wrote out all possible samples of 10 people, and we calculated the mean of each of those samples, and then we created a histogram for the possible samples of 10 people. In that case, since 10 is a pretty small sample size, the sampling distribution would actually follow a skewed shape, just like the population, or at least a skewed shape similar to the shape of the population. Now what if I wrote out all possible samples of 20 people, and I calculated the mean of each possible sample of 20 people, and then I created a histogram with the possible samples of 20 people. Since the sample size is going from 10 up to 20, this sampling distribution will actually be more normal than this sampling distribution. So it might be something like this. I'll try to draw an example. So maybe it's a little bit more normal, but it's still sort of skewed to the right. So if the population is if the population is skewed, then the sampling distribution will also be skewed if the sample size is small, meaning if the sample size of the possible samples is a small sample size. But in this case, when the population is skewed, the sampling distribution becomes more normal when the sample size of the possible samples increases. So I'm saying that the sampling distribution for samples of 20 people would be more normal than the sampling distribution for samples of 10 people, because 20 is a larger sample size than 10. Now what if I wrote out all possible samples of 30 people and calculated the mean of each possible sample of 30 people, and then I created a histogram of the possible samples of 30 people? Since 30 is a bigger sample size, this sampling distribution would be even more normal than this one. So if the population is skewed, the sampling distribution becomes more and more normal as the sample size increases. And if the population is skewed, then the sample size of 30 is actually the point at which the sampling distribution becomes roughly normal, even though the population that the samples are coming from is skewed. So they usually use 30 as a rough guideline for when the sampling distribution will be fairly normal, even though the samples are coming from a skewed population. Now you can imagine that it would be a lot of work to actually create these sampling distributions, because if the population is a city of 100,000 people, there would be many, many possible samples of 10 people. There might even be millions of possible samples of 10 people. And to create this histogram, we would have to calculate the mean of each of those possible samples, which would mean that we would be calculating the mean of millions of possible samples, and then we would have to put the means of all of those samples into a histogram. And that would mean that there would be millions of boxes in here, because remember, each box is one of the possible samples. And it would also be a lot of work to create this histogram, because there would be many, many possible samples of 20 people, and we would have to calculate the mean of each of those possible samples, and then we would have to put all of those samples into a histogram. So actually, all of these sampling distributions would be very hard to create, or even impossible, if the population is that big. It might even take a million years to create these sampling distributions. But in an actual research study, in which you're calculating the mean of a sample, you don't actually have to create the sampling distribution like we've been doing in our examples. What all you have to do is be able to predict the shape that the sampling distribution would have if you did create it. And it turns out that we actually can predict the shape of the sampling distribution because it's predictable based on the shape of the population and the sample size. We just found out that if the population is normal, all of the sampling distributions are normal for all sample sizes. If the population is skewed, then the sampling distributions with smaller sample sizes are skewed in the same way as the population. But the sampling distributions with larger sample sizes are more and more normal. And there's actually a name for the rule that we've just covered. It's called the central limit theorem. The central limit theorem says if the population is normal, meaning if the individual people in the population follow a normal distribution, then the sampling distribution is always normal. If the population is not normal, then the sampling distribution becomes more normal with larger sample sizes. And I said that if you have a skewed population and you sort the population into all possible samples of 30 people, and you calculate the mean of each of those samples, and you create a histogram of the possible samples, the histogram of the possible samples will be roughly normal, even though the population is skewed. Because I said that 30 is a rough guideline for when the sampling distribution of possible samples becomes roughly normal when the population is skewed. So let's see if we can use the central limit theorem to create a confidence interval for a sample from a big population. I'm going to write out a question up here that we'll answer together. Here I put up a confidence interval question that we can answer together. This is the type of confidence interval question that you would typically see in a statistics textbook, where it gives you a scenario of a person sampling a population and getting certain results. So here it says that a person is interested in estimating the mean height of a population of 100,000 people. So maybe this is the city of 100,000 people that we were talking about on the last slide. So the person is interested in what the mean height of the entire population equals. The person wants to know what number he or she would get if he or she was able to add the heights of all 100,000 people and divide the total by 100,000. But the person isn't able to ask all of the population members how tall they are, so the person can't calculate the mean of the population. So instead, the person asks a sample of 40 people how tall they are, and the person calculates the mean height of the sample of 40 people. So this person asks the 40 people in the sample how tall they are. The person adds the 40 answers and divides the total by 40 and gets a sample mean that estimates the population mean. And here it says that we're saying that the sample mean comes out to 62, meaning a mean height of 62 inches. We're also saying that somehow we know that the standard deviation of the entire population, meaning the population standard deviation, is 5.2. In an actual study, you never know what the population standard deviation equals. But I put it into this problem because we need to know what it equals to be able to use the formula I'm going to show you. And then later on, I'll actually tell you about how we deal with this issue of the population standard deviation in actual research. So we want to calculate a 90% confidence interval and a 95% confidence interval. Before we can do this, we have to look at this information and decide if the sampling distribution follows a normal distribution. Meaning we have to think about whether the distribution of the means of the possible samples that we're drawing from follow a normal distribution. Well, I said that the central limit theorem says that if the sample size is at least 30, then the sampling distribution will be roughly normal, or at least roughly normal, regardless of what shape the population has. I showed you back on this slide right here how when you're selecting a sample of 30 people from a population, the possible samples that you're drawing from follow a shape that is at least roughly normal, regardless of whether the population is normal or if the population is skewed. What I actually said was that if the population is normal, the sampling distribution will be normal. And if the population is skewed, then the sampling distribution will be roughly normal because of having a big enough sample size. So we know that we're dealing with a shape that's at least roughly normal. So I'll draw the shape of the sampling distribution, and let's look at the z table. Let's look at this table right here to look at what our confidence coefficient will be. First, I'll actually write out the formula that we're going to be using for the confidence interval. So it's actually the confidence interval formula when the population standard deviation is known. I should also say confidence interval formula for a mean when the population standard deviation is known, because here I'm saying that we know what it is. And this is the formula. And I said before we can use this formula at all, the first step is checking whether the sampling distribution has a normal shape. And I said that if a population it doesn't follow a normal distribution, then the sampling distribution will be at least roughly normal because of our sample size being at least 30. And in a research study, it's good enough for the sampling distribution to be about normal. You can't expect it to be perfectly normal. So since we know that the sampling distribution is definitely at least a roughly normal shape, then that's good enough. And we know that from checking the sample size. So let's think about what our confidence coefficient would be when the sampling distribution has a normal shape. Then the confidence coefficient for a 90% confidence interval is 1.645. Remember that this right here is the confidence coefficient. So our confidence coefficient is 1.645 for the 90% confidence interval. I could label this as confidence coefficient with a CC. And then this right here is the population standard deviation. In the question it says that it's 5.2. And we're dividing it by the square root of n. N is 40, because I'm saying that we have a sample of 40 people. Remember that this is the same formula that I showed you in the last video when we worked through my example with a population of 5 people. Now we're actually making use of this formula in a different type of question. This entire part of the formula that comes after the plus or minus is called the margin of error. But this part right here is called the confidence coefficient. So we have to, first we have to work inside the parentheses. We need to find out what the square root of 40 equals. It's about 6.32. So we need to divide 5.2 by 6.32. That'll be our next step. The first step was the square root. The next step is dividing inside the parentheses. So let's divide right now. What's 5.2 divided by 6.32? It's, well, it's about 0.82. So now we have 1.645 times 0.82. Once we multiply, we have the margin of error. And it's about 1.35. So let's take a look at this graph for a second. Let's imagine that 90% of the samples are between these 2 points. And since we know that our sampling distribution of possible samples follows this type of shape, we know that the confidence coefficient, meaning the z-score at this upper boundary, is the value that comes from our table, which is 1.645. That's the z-score at this boundary right here. And by multiplying that z-score by this right here, we get the margin of error. So the population mean, which we're estimating, we don't know what it is at the center. Remember how the population mean is at the center of the sampling distribution? We were able to see that in some of the examples I did earlier. And we also saw earlier that the margin of error is the distance from the population mean to this boundary point out here at the boundary of the middle 90%, at the outer boundary of the center area. So it turns out that this is 1.35. Remember that the distance to this boundary is the same number. In our other examples, we saw that they're the same number. So this 1.35 is our 90% margin of error. It's the distance from the population mean to the two boundaries of the middle 90%. And since this is our margin of error, this is what we add and subtract from our sample mean. So I said that the mean of the sample came out to 62. So let's add and subtract 62 and 1.35. Well, when we add, well, first let's subtract. When we subtract, we get 60.66. And when we add, we get 63.35. So our 90% confidence interval goes from 60.66 to 63.35. And you might sometimes see a question in the textbook that'll ask you to calculate the confidence interval and also ask for you to say how confident you are that the confidence interval includes the population mean. Meaning it might ask you, how confident are you that the population mean that we're estimating is actually between these two numbers? And your answer would be 90% confident. Your answer would be the same percentage. The reason why you're 90% confident is because remember that if you're creating a 90% confidence interval, it'll only include the population mean at the center if the sample that was selected is inside of the middle 90%. If the sample that we selected here with the mean height of 62 is in the lower tail down here, in the lower 10%, then the margin of error won't reach the population mean. It'll come up short, and the entire confidence interval will fall below the population mean. We saw, I drew this for you in another video when we were dealing with a small population. If this sample that we're talking about with the mean height of 62 is in the upper tail, meaning if that sample is one of the upper 10%, then the margin of error will come up short when you add and subtract, and the entire confidence interval will be above the population mean. But if the sample that we selected is one of the middle 90%, then in that case, the population mean will be inside of the confidence interval. For example, if this was our sample right here, with where this x is, then the margin of error will be long enough to reach over the population mean. So we're 90% confident that the population mean is inside of this confidence interval because we know that as long as we were able to get a sample from the middle 90%, our confidence interval would include the population mean. And when you randomly select a sample from a population, there's actually a 90% chance or probability of getting a sample from the middle 90%. Which means when we randomly selected our sample, there was a 90% chance that our sample would be one of the middle 90%. So that's why we're 90% confident that we ended up with one of these samples in here that would give us a confidence interval that crosses over the population mean. Now, what if we wanted a 95% confidence interval? Well, then we would do all of these steps the same way. The only difference is we would replace this z-score right here with the z-score in the 95% row. So this 1.645 would become 1.96. And then all of the other steps would be the same. And if you do this, you'll actually notice that the confidence interval down here will end up being wider than the confidence interval up here. Because remember I said that as the percentage goes up, the confidence interval gets wider. So you might be wondering, what would make this 90% confidence interval wider? What would make this narrower if we wanted to make it narrower? What if we still wanted to create a 90% confidence interval, meaning we don't want to change the percentage, but we want to make this confidence interval narrower so that it better estimates the population mean? Well, if you use a bigger sample size, such as a sample size of 50 or 60, for example, then what happens is the n in the formula goes up, and then what that does is that makes the entire margin of error that you're adding and subtracting smaller. So when the n goes up, the margin of error gets smaller, and what that does is it makes the confidence interval narrower. So the width of the confidence interval also depends on the sample size. It becomes narrower as the sample size goes up. And the next thing I wanted to show you is how a researcher would create a confidence interval if the researcher didn't know the standard deviation of the entire population, because in an actual research study, you never know what the population standard deviation is, because um, the only way that you would be able to calculate that is if you had data from the entire population, which you don't have in a real study. I just need a second to clear this off so that I can put a new question in here. Now we have a different question. The person is still interested in estimating the mean height of the population of 100,000 people, and the person is still selecting a sample of 40 people to collect data from. But now the person doesn't know what the standard deviation of the population is. Just like how in a real research study a person wouldn't know what the population standard deviation is. What this person does is that the person calculates the mean and standard deviation of the sample, meaning the person uses the 40 heights that have been recorded from the sample and uses those numbers to calculate the sample mean and sample standard deviation. And the sample mean comes out to 62, and the sample standard deviation comes out to 5.2. So this is what a person would be doing in a real study. He would be calculating the sample mean and the sample standard deviation. How do we calculate a confidence interval when we have a sample standard deviation instead of a population standard deviation? You have to use a slightly different formula. So here's CI, confidence interval formula for a mean. But now the population standard deviation is unknown. Meaning only the sample standard deviation is known. The first part is still the sample mean, the x bar, but the z-score turns into something called the t-score. I'll explain what that means. This alpha over 2 is just a subscript. What this subscript is saying is that this is the value that's at the upper boundary of the middle area, meaning it's saying that this isn't just, it's not just any z-score or any t-score, it's the value at the upper boundary of the middle area, meaning it's the confidence coefficient. So don't worry about this is just notation, because we saw this before when I had the z-score, and now we're seeing it again. We also have the second part, which is the standard deviation over the square root of n. Now the standard deviation is a sample standard deviation instead of a population standard deviation. And the t-score is pretty much an estimated version of the z-score. So now let's, instead of having a z-table, you have to have something called a t-table, and I'll get that for us. Here we have the t-table. What we need to do is we need to go to the right column for the confidence interval that we're creating. I said we're creating a 90% confidence interval, so we would go down here to the bottom and look at where it says 90%. This is the type of confidence interval that we're creating. And then we would you would go to the row that we need to go to get our t-score. The row that we go to actually depends on our sample size. We can see that our sample size was 40 because we have a sample of 40 people. The way the table is set up is that the row that we need to go to is actually the row that's one less than our sample size. because you'll notice if you go back to the table that up here at the top of the t-table, at the top of this left column right here, it says df. And what df actually stands for is 1 less than the sample size. So df equals n minus 1. And what would that be in our example? Well, we have a sample size of 40. 40 minus 1 is 39. So we would need to go to the 39th row. And we would need to go to the column down here that says 90%. We would need to go to the column that has 90% at the bottom down here. So it's where these two meet up with each other. And if the table doesn't have 39 in the df column, we'll just go to the next lower one, which is 30. So now let's go back to the table. There is no row for 39, so we'll use 30. So we want the 30th row, and we're creating a 90% confidence interval, which is right here. So we get where these two meet up is 1.697. Remember, we're using the 30th row because we were supposed to use 39, but they don't have 39, so we just went down to 30. So 1.697. Now let's actually use that value. So our sample mean is 62. The t-score that we got from the table is 1.635. I think that's correct. Let me double check. Oh, it's actually 1.697. What we would plug in over here is the sample standard deviation, because S is sample standard deviation, and the question is telling us that it's 5.2. 5.2 goes right here. Then the square root of the sample size, well, n is 40 because we have a sample size of 40 people. The person is using a sample of 40 people, so n is 40. N is just the number of people in the sample. So what we do now is we just do the same steps we did last time. We find the square root, we divide in the parentheses, then we multiply by this number, and then we add and subtract, and we get our confidence interval. And if you wanted to create the 95% confidence interval, you would do the same steps we did here. The only difference is this number out here wouldn't be the same number. If you wanted to create a 95% confidence interval, you would go to the column that says 95% at the bottom, and we would still use the same row because our sample size hasn't changed. So we're still using the same row we used before, but now we're using the 95% column. So our df would still be 40 minus 1, which is 39. I said when we would just go down to the 30th row. But now, if you're creating a 95% confidence interval, you would use the this column right here that says 95%. And one thing I didn't talk about at the beginning that I should have said is we still need to know whether our sampling distribution is normal, or at least roughly normal. And it would be because our sample size is at least 30. When the sample size is 30 or higher, then the sampling distribution is at least roughly normal. So that's something that we have to check at the beginning of the question before we start creating the confidence intervals. If the sampling distribution isn't at least roughly normal, we actually aren't supposed to be creating these confidence intervals. And you might be wondering why we would have to switch the z-score for the t-score. The reason is because when you replace the population standard deviation with the sample standard deviation, it can throw off the margin of error, because if when you substitute with the sample standard deviation, the sample standard deviation usually isn't the same number as the population standard deviation, and that throws off the margin of error. And since it throws off the margin of error, you risk the possibility of it ruining the confidence interval, meaning you risk the possibility that the confidence interval will no longer include the population mean. And in order to make up for that possibility, what you do is you switch the t-score, the z-score, for something called a t-score, and the t-score is usually a bigger number than the z-score. So by using a bigger number here, you make the margin of error wider. So by replacing the z-score with a t-score, which is a bigger number than the z-score, you make the margin of error wider, which makes you make the margin of error larger, which makes the confidence interval wider, and that way you can make up for, or you can prevent, or at least try to prevent that problem of the confidence interval no longer including the population mean. So by substituting the z-score with the bigger t-score, you make the margin of error wider, which helps deal with that increased risk of the confidence interval no longer capturing the population mean.